Hi everybody, this is Dr. Bricker here with a video for Chapter 21. So I will make two videos for Chapter 21. This will just be part one. So with Chapter 21, we get into something called electrical potential. So if you've heard about electricity, which I'm sure you have, you've heard of the idea of voltage. So electrical potential is the same thing as voltage. So when you see electrical potential here, really it means voltage. It's just another technique we can use to solve problems. So in this picture you see a brain that has electrical activity, and different areas of voltage have different colors, and we'll see how that works out in this chapter. So the goal of the chapter is to use electrical potential, or in other words voltage, and this idea of electrical potential energy. It can be confusing. They are not the same thing, but they're related to each other. So electrical potential, think of that as voltage. Electrical potential energy is energy of position. So just like in the energy chapters in Physics 220, we had gravitational potential energy, which existed between objects that had mass. For example, the Earth and some mass on the Earth had gravitational potential energy. We get electrical potential energy when we have separation of charges. So a similar idea, actually. So the voltage of a battery is the difference in electrical potential between its terminals. So voltage associated with the battery here. So we'll learn how an electrical potential is created, or in other words, a voltage is created when positive and negative charges are separated. So that's how we can create electrical potential energy. Okay, so we saw we could create an electric field, and we'll have electrical potential energy. In Physics 220, we had gravitational field, G, 9.8 newtons per kilogram, and we also had gravitational potential energy. So we have something we can fall back on. We've kind of have learned this idea in terms of masses. Now we're going to take the same idea and apply it to electricity. Okay, also in this chapter are capacitors. We've talked about capacitors already. This is actually a cylindrical capacitor, these different items here. We've talked about parallel plate capacitors in the past. I mentioned cylindrical capacitors, but haven't really seen a picture of it until now. So remember, capacitors store charge and create an electric field. We'll extend that idea. Capacitors also have a potential difference between the different plates, and we can store energy in a capacitor. Okay, so this is what we did previously. This was a positive charge. It has electric field lines. It's positive, so the electric field lines radiate away from the charge. We're going to have things called equipotential surfaces where the voltage is all the same. So that's what these green lines, green dashes are. These are areas that have the same voltage. This kind of maybe looks like something that you have seen before, an elevation chart, a topographical map. It's the same idea. When these equipotential surfaces are closer together, there's a steeper drop-off in voltage, just like on a topographical map. If you remember, if the lines are really spaced close together, that means that's really steep. On a topographical map, when you see a line like this means the same elevation. So the analogy to this is the same voltage. Okay, so more about that in just a minute as well. So Section 10.4, this was the energy chapter, if you remember. You learned that it's possible to store potential energy, we called it gravitational potential energy, between masses. Usually it was the mass of the Earth and something that has mass on the Earth, like this roller coaster, for example. So as the roller coaster goes up here, it loses kinetic energy, gains gravitational potential energy. We'll have the same idea with this chapter. We can turn electrical potential energy into different forms of energy, like kinetic energy, for example. Okay, very nice. So potential energy and electrical potential, related to each other, but they are not the same exact thing. Okay, so conservation of energy was a tool that we used before. We looked at the energy in one location. It was the same total amount of energy that we had in another location, but maybe the heights changed. We were able to potentially take gravitational potential energy, turn it into kinetic energy, and vice versa. The total amount didn't change. So conservation of energy just meant the total energy didn't change. It was kind of like doing accounting back in Physics 220. It's the same thing here. We'll just have a new kind of energy called electrical potential energy. Okay, so in this picture, the hand is doing work on the book, and the book gains gravitational potential energy. So we can have the same thing, and we will have the same thing in this chapter. Okay, here was a spring. The hand did some work on the spring, low spring potential energy, elastic potential energy we called it. This is higher. So you do some work on the spring, you store energy in the spring. We can do the same thing in this. We'll have energy stored in an electric field. Here, the energy is stored in the gravitational field. Okay, here it's stored in the actual spring. Okay, so let's take a look at this picture. Electrical potential energy and electrical potential again. So a charge is repelled by a stationary charge. So this is kind of like a spring, actually. A spring doesn't want to be compressed, but you can still compress it. This positive charge here does not want to be by this collection of charges. So pretend these are glued down in place somehow. And the charge is here, this separate charge. You want to put it here. It doesn't want to go there. So if you push it that way, you do some work on it. If you do work on it, just like the book analogy, you store electrical potential energy. Now, if this hand were able to let this go, the charge would go flying back the other way, just like a spring would open up. So the change in electrical potential energy is equal to the work that you do. Now, the tricky thing about electricity is we've got positive and negative charges. If this little q over here were negative, it would want to go over here. You wouldn't really have to do any work. So the work that you would do would actually be negative there, because a negative charge would want to go here. Our brains usually work in the positive, so I usually start with a situation like this. Okay, so the spring analogy is perfect here. Okay, so the energy is called electrical potential energy. So the U means potential, and then usually we just write ELEC for electrical. Okay. And then you can figure out how much you've stored by looking at how much work you had to have done here. Okay, so more about that in just a minute. Okay, so source charges alter the space around them. So it's calling these the source charges. These are somehow glued down. So these have an electric field all around them. We saw that from the previous chapter. And you could actually calculate it for these point charges. The electric fields are tough to work with, though, because they're vectors. You have to figure out the direction of the net electric field at different points. And it would be pretty hard to do. Not impossible, but you could do it. You know, you have to take into account which direction is the electric field from, say, this charge here. What's the direction of the electric field maybe at this point from this charge, and you could add them all up. You have to do the X part separately from the Y parts. Now, the nice thing about electrical potential, or in other words, voltage, it's just a number. There's no direction associated with it. Just like we could have thought about gravity as having kind of a gravitational potential, and that would just be a number. Okay? So we will have a way to look at this, where if we just knew the electrical potential here, and we knew what kind of charge we wanted to put there, we could figure out how much energy is actually stored there. So that's the goal of this. Just have a number at, say, this point P, called the voltage, and if you knew how much charge you wanted to put there, you could know how much energy is stored, or in other words, how much work you'd have to do. Okay? So in order to do this, we need to figure out the potential energy that would be at a near point, so near this source charge. And let's see how that's actually going to work out. So let's say we had 10 nanocoulombs here, and we just say that the electrical potential energy at point A is 0. So this is really far away. And we could do that. You could set the reference point to whatever you want. It's the difference in electrical potential energy that we're worried about, not the actual amount. That's how we did physics 220. If you remember, the ground we said was 0. Anything above the ground in terms of gravitational potential energy was relative to the ground. Okay, so to find this charge's electrical potential energy at any point, you can measure the amount of work it takes to move it from, say, point A to another point. So start here. Here's how much charge it is. How much energy does it take to move here? or I should say, how much work does it take to move here, or how much work does it take to move there? And these are just glued into place, right? This is a positive charge. It doesn't want to be over here. It would rather be really far away. They don't like to be by each other. Okay, so when you're looking at a battery and you get electrons to flow, you know, why do electrons flow? They don't want to be by other electrons, so you can get them to flow through a wire. This is a positive charge, so we don't have electrons. It's just a positive charge, lack of electrons. It's the same idea, though. It doesn't want to go over here. It would rather be here. So that's the fundamental idea behind electricity. Okay, so if it takes 4 microjoules of work to move it from A to B, from here to here, and if it takes 6 microjoules, remember joules, that's the unit of energy, we could figure out the potential, the difference in energy between these different points, right? If this is 4 and this is 6, the difference between here would have to be 2. So if we were to have 20 nanocoulombs, then according to the Coulomb's force law, you remember Coulomb's force law is the force between charges, between different charges, is Q1 times Q2, the magnitude of those, divided by the distance between them squared. So if you had 20 nanocoulombs, the force is going to be twice as much as if you had 10, so a hand would have to do twice as much work as the if you compared 20 nano to 10 nanocoulombs. So the charge's potential energy is proportional to the charge, just like the gravitational potential energy we saw from physics 220 was proportional to how much mass you actually had. Okay, good. So we've seen from the previous slide the difference in potential energy between two spots, two different locations, just like we had, remember in physics 220 with gravitational potential energy, if it took you a certain amount of work to go to a certain height and then more to go to a different height, you could figure out the difference between those two. And that's what really we were worried about, was the difference in energy. So we'll have the same idea here. So we see the difference in energy. Here we see that the potential energy that you have, electrical potential you have, is proportional to how much charge you have as well. So if the electrical potential energy for a charge of 10 nanocoulombs is 4 microjoules at a given point, the electrical potential energy would have to be twice as much, or 8 microjoules for 20 at the same point, and 2 microjoules for 5 nanocoulombs. It's all proportional. So let's look at the energy per charge at different locations then. That's what voltage is going to end up being. Voltage is the amount of energy divided by the charge. So 2 microjoules would be 5 nanocoulombs, 4 microjoules, 10, you know, it's proportional. Okay, so what we end up getting, if you look at this, that location would be 400 joules per coulomb. So if you knew how many coulombs you put there, you would know how much energy. This here is actually the voltage. Let me circle it. This is the voltage. So a joule per coulomb is a volt, it turns out. So the amount of energy per charge is the voltage. So you can start to see why this is useful. If at a given location in space you knew the voltage, or how many joules per coulomb that spot represented, if you put a certain amount of charge into that spot, you would have the energy there. Okay, so let me write this a little bit better. The amount of energy is the charge times the voltage. And that's the use of this. If you knew the voltage at a given spot, and you know how much charge you want to put there, you'll see how much energy you have. So a joule per coulomb is a volt. And there's nothing to do with vectors here. That's, again, the nice thing about it. There's no absolute value sign on Q here, so the energy, this could turn out to be negative. The voltage could also be negative. Okay, so we'll have to get some practice with that. Again, no absolute value sign here. Oh, and there's the formula. Good. And then a volt is a joule per coulomb. Okay, so we're still looking at everything in a macroscopic way. We're building towards looking at actual circuits where charges are moving. Okay, and we'll see more with voltage when we do that. Okay, so I've already talked about the topographical map idea. So points that have the same voltage are at the same height. So a little bit more about this actually. So topographical map analogy is if you have the same voltage, you're at the same height. So if you have the same height and you tried to put some mass at the same height, you'd have the same gravitational potential energy. So if you have the same voltage and you have a surface that has the same voltage, you would have the same amount of energy stored there. So for example, let me draw a little map here. I'm trying to draw a kind of a topographical map. Okay, so these, it looks just like a topographical map. These are equipotential surfaces. So equi means the same potential. So you could take a charge, put it here, or put it here, put it here, put it here, wherever you want to on this equipotential surface diagram. You would have the same voltage. It would take the same amount of energy to put a charge anywhere where you have the same voltage from the formula that we saw. U is equal to Q times V. Okay, excellent. We'll have to get some practice with this. This is a lot of theory right now. Here are some typical potentials, or in other words, voltages. EEG 10 to 100 microvolts, so really small. Cells in the human body 100 millivolts. Batteries 1 to 10 volts. Your car battery has 12 volts. Electricity, these are just orders of magnitude. 120, or sorry, it's really 120, but here 100 volts approximately. Static electricity, you can build all the way up to 10 kilovolts. Okay, so where would that happen? You know, maybe if you had like a thunderstorm going on, lightning, or transmission lines all the way up to 500 kilovolts, so 500 times 10 to the third volts. Okay, just so you have an idea of the different scale here. Here's an example we can take a look at. 15 nanocoulombs, so 15 times 10 to the minus 9 coulombs charged particle moves from point A, where the potential is 300, to point B, where the potential is negative 200. By how much does the electrical potential change? Okay, so what does that mean, electrical potential? What are the units of it? Think of it as voltage, and the units of voltage are volts. How much does the particle's electrical potential energy change? So this is different. This is electrical potential energy. Okay, that's measured in joules. Electrical potential, or in other words, voltage, is measured in volts. And then how would your answer differ if the particle's charge were negative 15? Okay, let's take a look at this. So the change in electrical potential is the difference. It's the final minus the initial. That's what difference means. Final point, which is B, minus the initial point. Okay. We can find the change in electrical potential energy by using the formula that we just came up with. It wasn't written as a difference formula before, but you can do it like that. We had this before. U is equal to Q times V. Delta U would be equal to Q times delta V. Okay, so that's what we'll use for the second part. Okay, so the difference in voltage is minus 500. This change is independent of the charge. It's just a number there. Remember, it's volts. What do volts actually equal? Joules per coulomb. That's what a volt is. So think about it like that. So if a volt is a joule per coulomb, multiply a volt by the amount of charge, you get how much energy you have stored there. Okay, and that's what's being done here. Here's the charge, here's the voltage. You can figure out how much energy is there. Now if you replace the charge with negative 15, this turns out to be positive 7.5. Okay, so this positive charge going through this negative voltage difference, it wants to do that. You don't have to actually supply any energy. Here, on the other hand, this negative 15 does not want to go through this scenario. So you have to supply energy here. Okay, you have to think about the negative sign with voltage. Okay, because the electrical potential at B is lower than at A, the positive charge will lose electrical potential energy while the negative charge will gain energy, electrical potential energy. Okay, very good. Sources of electrical potential. Well, we've talked about capacitors before. We'll use capacitors again. So how is electrical potential created? Well, you have to have, one way of doing it anyway, is to have a separation of charge. So the force on charge Q is 0. So right now you could move it wherever you want to. No work is needed to go from A to B. So there's no potential difference between A and B. It doesn't necessarily mean there's no potential, it just means there's no potential difference. There's no voltage difference there. So if electrons were transferred from the right side of the capacitor to the left side, giving the electrode a negative Q and the right electrode positive Q, the capacitor would have no net charge, but there would be a charge separation. So we're charging up the capacitor, just like this. So you've taken negative charge from this side, you moved it over to this side. And you keep doing that. That leaves this plate positively charged, this plate negatively charged. We've created an electric field between here. So if you take a positive charge, it doesn't want to go this way. It's going uphill. It's going from a lower potential to a higher potential. It doesn't want to do that. You store energy. Now if you move it over here, you don't make it all the way across, you let it go, it's going to go flying back the other way. So we could take that electrical potential energy that we had stored and turn it into kinetic energy. Okay, so you could separate charge. That's how you can create a difference in electrical potential, or in other words, voltage. Okay, so metal wires are attached to the terminals of a 3-volt battery. What's the potential difference between point 1 and 2? So we don't know this about wires yet, but this wire, we're going to assume it doesn't have any resistance to flow at all. So this wire could be as long or as short as you want it to be. So basically you're connecting it here and here. We could cut this here, and we could cut it here if we wanted to, and then just pretend what's the difference between this point, I'll call it A, and this point B. And it's just going to be 3 volts. So we don't quite know this yet, but this is a conductor. Charges easily could move through a conductor, so there's no potential difference in a conductor. This would be like walking along the same surface. We could move electrons through wires for free if there's no resistance, if they're a perfect conductor. In real life, that's not how it works, but relative to other paths, wires have really low resistance. Not 0 usually, but really low. Okay, so we're just measuring the voltage across the battery. So as you shuffle your feet across the carpet, friction between your feet and carpet transfers charge to your body, causing a potential difference between your body and a nearby doorknob. So you know what happens when you go to touch a doorknob sometimes. You get a shock. So charge moves from, say, your finger to the doorknob. There's a potential difference developed. Okay. You can see the potential difference with the clouds here, something like 10 to the 8th, so like 100 million volts or something here. So lightning is the result of charge separation that occurs in clouds. Small ice particles in the clouds collide and become charged by frictional rubbing. If you've done the first lab, you know you could actually do that pretty easily. Heavier particles fall to the bottom and gain negative charge. Lighter particles move to the top and gain positive charge. There's a difference in voltage. Negative charge on the bottom of the cloud causes positive charge to accumulate on the ground, through induction. So this part of the cloud is negatively charged. That induces electrons on the surface to go further in, leaving this positively charged. And electrons in the cloud then are attracted to the positive charge here. So electrons in the cloud go to the surface. That's what lightning is. Good. So a battery creates a fixed potential using chemical processes. So we've seen a capacitor, you can separate charge, set up an electric field and a potential difference that way. A battery, through chemical processes, maintains a voltage across it, but eventually batteries even wear out. Okay. In biology, chemicals produce a potential difference of about 70 millivolts between the inside and outside of cells, depending on what they're made out of, calcium ions and potassium ions, things like that. You probably have encountered that in biology already. So the membrane potential of a cell is caused by this imbalance. Oh, here it's potassium and sodium. Sometimes calcium is involved as well. Okay, so diffusion tends to equalize the concentrations just by the number of that we have. And you could also have a sodium-potassium pump separating charge using energy from something called ATP. So more information than you might need here, but maybe you have seen this in biology. So many of the physics parts of class you see, and definitely in engineering and technology, but really it comes into play in biology a lot too. So how do you measure electrical potential? Maybe you have one of these at home. I've got a couple of these at home from projects I do around the house. So this could measure a lot of different things. Here we're measuring actual voltage. So this is set on something called DC volts, and we're measuring the voltage across this, used to call them transistor batteries. So this is about 10 volts or so. Okay, good. So this image is a micrograph of a nerve cell whose membrane potential is being measured. So we're actually measuring the potential across the cell. A glass pipette filled with conducting fluid is inserted through the cell membrane, and then the second probe is immersed in a conducting fluid that surrounds the cell, and you could actually measure the voltage that way. Okay, and we will, I'll make a separate video going over some of the homework when we talk about those problems. Okay, so this is kind of the theory today. So electrical potential is created by separating charges. We've seen that. Capacitor is a great example of that. So you get a voltage difference. So don't forget, a volt is a joule per coulomb. And you can take this energy that you stored and do things with it. So with going back to physics 220 again, if you have a spring, you can store energy in a spring and then utilize it later. Gravitational potential energy, you could lift a mass up, have it there, and then later on let it go, and you change gravitational potential energy into kinetic energy. We can do the same thing with electrical potential energy. We can turn it into kinetic energy. We can get things to move. So you can store energy, electrical potential energy, to use later. That's what a battery is doing. That's what a capacitor is doing. So if you charge up a capacitor, you store energy that you use later. I've got a light I take camping. I just can move the pulley that's in it, the little lever thing that turns, and it stores a lot of energy there. I'm actually producing charge and charging up a capacitor, and then when I turn it on, I use the energy, the electrical potential energy I've stored, I turn it into light. So this is conservation of energy. This is what we've seen before in class. So the initial energy is equal to the final energy. Actually, it's written here, final energy is equal to the initial, but that's okay. It's the same idea. So the total final energy, that's supposed to be an F. Okay, there we go. Is equal to the total initial energy. Now the initial energy, or the final energy, whichever you want to talk about, is made up of kinetic and electrical potential. So that's where this is coming from. So in physics 220 we use Ke for kinetic. So kinetic final plus electrical potential final is equal to kinetic initial plus electrical initial. And then electrical initial is this, Q times V. Electrical final is same thing, Q times V final. I use Ke for kinetic. The book uses K, but it can be kind of confusing if you have a spring with spring constant K. So I'm going to stick with using Ke for kinetic. Okay, so we're just looking at the energy we started with being equal to the energy that we end up with. It just might change forms, you know, from kinetic to electrical potential and vice versa. Okay, so the change in kinetic energy, this is from Physics 220 as well, is equal to minus the change in potential energy. And the new stuff that we have from this chapter, this is minus Q times delta V. So whatever you gain in kinetic, you lose in electrical potential energy. This really is from Physics 220. This is the new part here, the electrical way of looking at it. So when the change in kinetic energy is positive, particles speed up, they gain kinetic energy. When they slow down, they are losing kinetic energy. So remember what kinetic energy is. 1/2 mv squared. Now be careful, this is little v, that's for velocity. I guess I should just call it speed here. This is big V, that's for voltage. So make sure that you know the difference between those. When you start to maybe make a little note card for yourself, you have to know what these things are. This is velocity, meters per second. This is voltage, measured in volts. Okay, so let's see what we have here. Here's a region where we have 500 volts. Here's a region where we have 400 volts. Now a positive charge will go from higher potential to lower potential. It will want to speed up. So we're going from 500 to 400. That would be like going from a higher elevation to a lower elevation. So a positive charge would speed up there. Okay, a negative charge would not want to do this on its own. Okay, good. Excellent. So a positive charge slows down when you go from, for some reason, if you had a charge here and it moved over there, it would slow down. You couldn't just put a charge here. You couldn't just put a charge there and have it scoot across. This would have to be a situation where it was already moving here. So somehow it's already moving, encounters this region, and then it would slow down. In the previous slide, if you put a positive charge here and it wasn't moving, it would scoot across here and speed up. Here, this one can't start at rest. It already has to be moving at that spot, and then it would slow down. This is like a mass going uphill. Okay, so electrical energy can be transformed into lots of different other kinds of energy in addition to kinetic energy. You can connect it to a light bulb. The energy is transformed to thermal energy in the bulb, making the bulb glow as electrons move through, heating up the filament in this bulb. Okay, so let's see. A positive charge moves as shown. What happens to its kinetic energy? Well, pretend that you had this charge here. Would it want to go across? Right, the electric field, I'll use red for the electric field. This is the electric field. This is from physics, or chapter 20. This is going to have equipotential surfaces that look like this. Here we're going from a lower voltage to a higher voltage. We're going uphill. That's one way of looking at it. This charge does not want to move to the right. It's happy where it's at. So if it were to move from where it's at over to the right somehow, its kinetic energy, what would it be doing? It would have to slow down. It doesn't want to go there. It would slow down. So the kinetic energy would decrease. How could this actually happen? How could you have this scenario? So if you had one plate like this and one plate like this, and I purposely drew a hole in this plate, you'd have to somehow inject this charge this way, and then it would encounter the electric field and slow it down. Okay, good. So the kinetic energy decreases. What happens to it? It turns into electrical potential energy. Okay, so let's see what we have here. A proton is released from rest at the dot. Afterwards, the proton, okay, so this would be like going uphill, going from 0 to 50. This would be like going uphill, right, from a lower to a higher. So this proton, the key that it's a proton, it's positively charged. it would go in this direction. Another way of thinking about this, well, how are you going to actually create this? What if this was a positive plate of a capacitor over here? This was a negative plate of a capacitor. Maybe you could figure out some way of doing this, and then you would get it to move down and speed up. Okay, increasing speed and losing electrical potential energy. So an electron accelerated through a potential difference of 1 volt, gains kinetic energy. So we have got a change in kinetic energy minus Q delta V. We saw where that comes from. Now this, the charge of an electron, remember, is minus E, right? This really, maybe this should be like minus E there. The fundamental charge is 1.6 to the minus 19th coulomb. So if it's an electron, it's minus 1.6 to the minus 19th coulombs. Okay. So the amount of the change in kinetic energy then, if you just use the formula, the negative sign goes away. That's why you don't see a negative sign here, because it was negative Q, but Q is already negative, so that goes away. Anyway, so then we've got the charge times the voltage, 1.6 to the minus 19th joules. So we'll come back to this unit later in the semester, but this is an electron volt. An electron volt is another unit of energy. So 1 eV is 1 times 10 to the minus 19th. Should be 1.6 times 10 to the 19th joules. So make a note of that. This should be 1.6 times 10 to the 19th joules. That's what 1 electron volt is. I'm not sure what happened to the 0.6 there. Okay, excellent. So we won't do too much with electron volts in this chapter. We will come back to it when we do modern physics. We measure the energy of different, maybe hydrogen atoms in terms of electron volts. We're looking at quantum physics, probably about week 14 or so. So a proton or electron that accelerates through a potential of V volts, whatever it is, has VeV. So if you take a proton and an electron that goes through 5 volts, it turns out to have 5 eV of energy then. So it's supposed to make our life easier. It does, you just have to get some practice with working with the electron volts units. If you don't like them right now, that's okay. We know the conversion factor, and we could always just change it back to joules. Okay. And then we will take a look at this on the homework video that I'm going to make. Okay, so for the first part of the chapter is using this idea of voltage. So remember, the energy is Q times V, and if you want, you could write it like this: delta U is equal to Q times delta V. The change in kinetic energy is minus the change in potential energy, so that can help us sometimes. So that would be minus Q times delta V. Or we have conservation of energy, where we had the initial kinetic energy plus Q times the initial voltage, that's the initial electrical potential energy, would be equal to final kinetic energy plus Q times V final. Now I can rearrange this formula. Let me do it like this actually. Let me put kinetic energy final on the right. I'm putting all the kinetic energies on the right. And then we put the other part on the left then. I'm going to write it like this though. Q V final minus Q V initial. Separate these. Okay, so this line was just conservation of energy. Now I put the initial kinetic energy on the right hand side of the formula. I put Q V final on the left hand side. I wrote it like this. Check it out, it's the same thing if you multiply the negative sign through. This is minus delta U. And then this is the change in kinetic energy. So when you see this formula here, it's just another way of writing this formula. Okay, the only other thing to say is don't forget kinetic energy is 1/2 mv squared, little v squared. So this is using voltage to figure out changes in potential energy, how much work you have. You can figure out how fast you're going after you go through a certain voltage, that sort of thing. Now the second half of the chapter are different situations where we actually can calculate the voltage. So that's enough for this video, figuring out what we can do with voltage. The next one, the next part of the chapter actually is, okay, we know what to do with it. How do you actually calculate the voltage? And we'll take a look at that. Voltage due to point sources, voltage due to capacitor, and then a little bit more detail into capacitor and energy stored in capacitors. Okay, any questions, email me, and I will talk to you soon. Bye-bye.